Well, but it's difficult to compare, right? Because I mean, now in Australia, it's summer. It's kind of close to summer, but here in the north part of, like, let's say in Europe, it's winter. So I guess also because of that, like the weather in Australia is much better than the one here.
Yeah, but even in summer in Europe, it's worse than summer here.
Oh, well, I mean, once you are used to it, I think it's okay, right? Well, I guess you just need to close all the curtains and the shelters and then just stay at home or get a nap during the summer and get through it, I guess. So do I have to share my screen or or the document? Which one do you prefer?
Can you please try to share screen? I think you can. I mean, it's up to you, but it would be best, I think, to share screen.
The screen. Okay, so I will open my file here, and then I will share the screen. Great. Here. So how much time will I have, if I may ask?
You have approximately 1 hour with questions. So can we interrupt you during the talk?
Great, you can feel free to interrupt. Okay.
And you have approximately 1 hour with maybe a discussion. Great. After this, if anyone wants.
Okay, so I'm going to share my screen. I hope everyone can hear me clearly and also see the screen like clearly, let's say.
Yeah.
So this is, okay, so great. So thank you, Anton, for inviting me to this international seminar. So today I'm going to present okay, first I need to introduce myself. So my name is Weifeng.
I can introduce you. So
okay, great, thank you.
Welcome everyone to the Center of Econometrics and Business Analytics seminar series. Today we are having Weifeng Jin from University of Barcelona with a talk about Quantile Autoregression-Based Non-causality testing. So welcome.
Great. Thank you very much, Anton, for the introduction and also for the invitation. So today I'm going to present my work on the Quantile Autoregression-Based on non-causality based non-causality testing. So before I move forward on to the testing part, I would first explain or introduce what is non-causality actually, because this is not a common knowledge to most people, even inside like time series community. So theoretically, it means that at least there is one root to the autoregressive polynomial which lies inside the unit circle. So let's look at a very simple L1 process. Usually we assume that this rho should be smaller than 1, the absolute value of rho. So there is no explosiveness and the result of the process is stationary. But once we allow for the non-causality, that means this rho can be larger than 1 and this becomes an explosive root. But anyway, there will be a stationary solution or representation to this kind of explosive process. And this is actually non-causality. And more specifically or more empirically, it means that the future plays a more important role in the determination of present value. So why should we care about this kind of non-causality, or what is the use of this non-causality? So in the current or existing literature, we have found that there are many applications of this type of process. So first, it can be used to display nonlinear dynamics like speculative bubbles and asymmetric cycles and volatility clustering with this kind of linear process. So we don't need to incorporate other nonlinear terms or components to characterize those nonlinear dynamics. With this simple model, linear model, we can actually display those nonlinear dynamics at the same time. That's surprising. And also, like this has been shown that it can improve the forecasting accuracy in macroeconomics and finance. Also, it can be working as an alternative to non-invertible process in modeling forward-looking behaviors, because it's kind of you take into account the future component, and once an agent, his expecting or her expectation of future is very precise, we can actually use the actual future value as a determination or determinant of the current value once when they make the decision. So what is the obstacle or the problem? So based on the second order moment with the current method, like OLS or Gaussian maximum likelihood estimation, we cannot distinguish the non-causal process with their causal counterpart. That leads to the failure of identification of non-causal process based using the traditional method. So in the existing literature, there are several estimation method or robust estimation method which are applied to this type of non-causal process. The first tribe is about to use non-Gaussian density function or maximum likelihood functions, like it's proposed by Bradit and Lee and Rosenblatt, that you can assume that the density function is known. Then you can implement non-Gaussian maximum likelihood estimation, and then you can achieve the identification and get the consistent estimation. But the thing is, you need to know the density function a priori, which is quite infeasible in the empirical cases. Or you can assume that the density function follows T, even though T student distribution, even though the true one doesn't follow this distribution, and then you implement this non-Gaussian maximum likelihood estimation, you can still achieve the identification, but there will be some constraint or restrictions in the assumptions for the ones that can be applied. Or you can also use this methodology to the alpha stable distribution, because we know that alpha stable distribution has this distribution preserving property that when you add up all the alpha stable distribution, you can still get an alpha stable distribution, and this attribute can be used to construct the density maximum likelihood estimation. Another tribe is to use the minimum distance estimation. It is first proposed by Gospodinov and Nier, and they use the information contained in higher order moments, like the third order moments and the fourth order moments or cumulants, to construct a distance and then try to minimize that distance to get achieve the identification and also the estimation. It also can be used like in the frequency domain, that the third order moments or fourth order moments, and also the characteristic functions or the CDF of the distributions. Once we impose ideas of the innovations, then we can derive some criteria, like some distance, to estimate the possibly non-causal and non-invertible models. But what about the test? The test for non-causality? There is no this kind of test existing in the current literature. The thing is, of course, we can implement the test for non-causality once we have the robust inference for the possibly non-causal AR process. But first, it requires the factorization of the coefficient to get to the original roots, because we know that the causality or non-causality is related to the roots, not related to the coefficient. So in the AR1 or AR2 case, we know that it's very easy to get the original roots by the factorization. But once the order gets higher, let's say AR3, AR4, then we can find out that the factorization or this kind of situation becomes very complicated, and sometimes you cannot get a precise or get a proper roots easily. So this could be a problem. And also because if we first need to rely on a robust inference of the estimation, then that means we need to confine to the assumptions required by this estimation technique. And usually these are more stringent than the usual estimation method, and that means it can be less generally applicable. And also, if we already have the consistent estimation robust to the non-causality, then the testing problem gets very trivial after this. I mean, we want to test it because we want to select a proper model for the causal case or the non-causal case. But if we already get the estimation, then that means it's kind of, we already done the job. So there is no meaning to implement these tests further, right? So there is no test for non-causality prior to the estimation is carried out. So we would like to come up with these tests without this robust estimation and use it as a model selection criteria. So for the existing literature on the estimation method, we get the information or message that more information needs to be employed to achieve the identification or to distinguish the causal and non-causal counterparts. So in this case, we're using the quantiles of the distribution. Since the third order moments or the first order moments can be applied, that means the quantile of the distribution, which contains more information than just third order moments or fourth order moments, is even sufficient, let's say, even better to achieve the identification or distinguishing of causal and the non-causal process. So in this paper, we propose 3 testing strategies for non-causality within the Quantile Autoregression framework. So this framework has been sophisticatedly developed, the inference study, the testing part. So we use these, we directly borrow this tool from the previous scholars, and so this methodology exploits the nonlinear attributes displayed by this non-causal AR1 process. So in this paper, with this methodology, we try to fill the gap of no test for non-causality in the current literature, and we don't need to assume any distributional assumptions for the innovations before we carry out the testing. And also this is robust to the mixed causal and the non-causal AR1 process that I'm going to introduce formally later with unknown order of non-causality. And this methodology can be possibly extended to AR process, accommodating different types of conditional heteroskedasticity. So before I move on to the official testing procedure, I will first introduce this type of more general AR process, which is called mixed causal and non-causal autoregressions. So now we have 2 orders, which one is R and the other one is S. So this moving average mixed causal and non-causal autoregression of order R and S process is defined by the similar way of the conventional AR process, but with 2 autoregressive polynomials. One is of order R, which is the lag operators, and the other autoregressive polynomials is about the lead operators of order S. So UT is ID innovation sequence with mean 0 and the variance sigma squares, which is finite. That is the assumption that we needed for the innovations. And also we need to assume that the roots to these both polynomials phi and psi lie outside unit root to guarantee the stationarity. And once this S, which is the order of this least operator, is greater than 0, that means there is non-causality existing in the non-causality existing in this process. And if and only if S equal to 0, which means this autoregressive polynomial of least degenerated to 1, then we call this process is purely causal. And the total number of the order, which is P, it's a summation of R and S, can be easily determined by the conventional method based on the second order moments like I or big. So we try to, this type of process is quite useful. And here I list several statistic properties of this type of, or this more general autoregressive process. So first is that the second order property of these mixed causal and non-causal autoregressions. We calculate the autocovariance generating function of this given MAR of order R and S. We can get that this GL will be equal to this term. And once we just by a very simple step, we can get this autocovariance generating function is exactly identical to their causal counterpart. And even more surprisingly, we can find out that for any combination of these orders R prime and S prime, as long as the summation is equal to the total order is the same, then YT shares the exactly same autocorrelation function structure. That's the reason why the second order moments fail to identify the causal part and the non-causal part. So there is also, by rewriting the representation of this general move MAR model, we can get a causal representation or causal representative of this process, which is just by multiply a causal polynomial in the left-hand side and divided by this non-causal polynomial in the right-hand side. And we can get this causal representative with the UT star is actually a white noise, which means they are uncorrelated, but they are dependent in higher order moments. So this is also kind of useful in the predictability in modeling financial returns, especially because this means that the model is linear, or the error term, the innovations is linearly unpredictable because it's white noise. So the covariance is 0, but it's non-linearly predictable. That means if we try to predict their higher order dependence, then this is actually doable. And this could be very useful in the forecasting or the predictability, this topic, or for the financial data. And the second property, statistic property of this is that it can be used to display local explosiveness or like the speculative, which is kind of a characteristic of speculative bubbles. So from these simple simulations that I'm going to zoom into to make it a better scene. So we simulate 4 MAR11 process with different parameters. And we can see that the trajectories vary a lot based on the choice of your coefficient. So the first in the top panel, in the top of this panel, we can see that you can find out these kind of local explosive behaviors in the first one and the second one, which is characterized by these several or repetitive upward trending, and then followed by abrupt sharp drop, like here and also here. And based on the choice of value, the different values, we can actually simulate different types of bubbles, like the mild one or very sharp one or very strong one. And also based on the choice of order of these MAR, we can get a very simple or very normal, like without any local explosive, like the stationary one, and which accommodates the other types of non-dynamics, like we usually characterized by the simple or conventional AR process. And there is another application, actually, it's about the conditional heteroskedasticity, but due to the limit of time, I'm not going to explain this example. If we have time, we can come back to see how this is able to display conditional heteroskedasticity. So we have seen several characteristics or the attributes of MAR, this process, and now this is an official definition or theory about the nonlinearity of this type of process. So we denote for the simplicity of further study, we denote that the information set observed up to the period k by this ik and the 10th quantile of yt conditional on the information set ik by the this notation. So the assumption that we need is quite regular. It's the one that used by the Rosenblatt in his proof of conditional mean of non-causal process is nonlinear in the past observations. So let this innovation sequence be non-Gaussian, because we know in the Gaussian case that second order moments can determine the whole probabilistic distribute or structure. So there is no meaning to distinguish causal and non-causal in the Gaussian case. But if the UT is non-Gaussian, that means they're actually different, and we need further information to determine their probabilities. And with k+1 order moment, finite moment, and k+1 cumulant non-zero for some k large greater than 2. This is a very regular, and actually to guarantee that there is finite variance and also distinguish them from the Gaussian case. So the theory one is based tells us the nonlinearity in the conditional quantile of non-causal process. So under the assumption one, which is the one that I explained before, the stationary MAR of order R and S model YT defined by the equation one is non-causal. That means S is not equal to 0 if and only if there exists a conditional quantile non-linear in the past observations for at least one quantile over the across the whole range of quantile range. And the proof is actually quite easy, and it is from the conclusion that, or the theory in the Rosenblatt, that the conditional mean of YT given the past information is nonlinear in YT. So there exists at least one conditional quantile which is nonlinear. Otherwise, when you aggregate them, it's gonna be linear. So we use contradiction to prove that there exists at least one conditional quantile which is nonlinear in the past. So in order to test for non-causality, we need to formalize the hypothesis. So the objective is that, on the null hypothesis, is that we need to test all the coefficients in the non-causal autoregressive polynomial equal to 0. That means that autoregressive polynomial degenerate to 1. And against the alternative hypothesis, which is the process is non-causal, that means there exists one per se coefficient or one root which is non-zero. So the causal AR or QAR p-order model for YT is actually fully exploited by a paper by Poenker and Shao in 2006, and they can just write this conditional quantile with this linear expansion, and we just denote by xt prime theta tau. And the estimate of the theta tau is actually obtained by minimizing this following objective function, which is a check function. And we can get the consistent estimator if the model is actually, the process is actually causal. Actually, this is not an original approach. In 2021, Heck and Sun, they already adopted this approach and used the residuals obtained from QAR model by running the regression with the direct time and with the reverse time, respectively, to compare the statistic of residuals to see which one yields a better goodness fit, let's say, and as a model selection criteria. But the thing is, with this approach, you can only distinguish purely causal and purely non-causal. But there are cases which is in the middle, like mixed causal and non-causal. So there are roots in the causal polynomial and there are roots in the non-causal polynomial. And in that case, with this approach, probably it's gonna give you misleading conclusions, because you can only run two regressions, one direct and the other one reverse. So with this approach, you cannot distinguish that for a mixed causal and non-causal case, which one is a better model. But in our approach, actually, we are able to distinguish this. So there is a conclusion from the theory one, which is like under the assumption 1, 2, 3. So the assumption 1, 2, 3 is actually the first assumption that we explained, and plus two assumptions which is required for the QAR estimation, and the null hypothesis, which means like the process is causal. The coefficient except the intercept in the QAR framework are constant across the different quantiles in the whole range. So that means we can translate the null hypothesis into all the coefficient equal to a constant over the different quantiles except the intercept. And or the alternative hypothesis will be there exist at least two quantiles that the estimates of the coefficient at those two quantiles are different. So this is the alternative is actually not proved. So the consistency of these test for non-causality based on this constancy test is actually not proved, because we don't know the true conditional quantile. It's going to be a very highly nonlinear functional form, and so far we are unable to prove to derive the correct or the explicit functional form of a conditional quantile for the non-causal process. But with following two reasons, it's very likely that we can conclude that coefficient in the QAR framework for non-causal process are varying over the different quantiles. The first one is that we have seen before in the examples, like a simulation example, like non-causal processes display asymmetric dynamics. So the asymmetry dynamics usually comes from that the coefficient in the AR models are actually not constant. And another one is that the linear quantile expression of this conditional quantile for the non-causal process is misspecified. So that means we need to come up with a nonlinear functional form for the specification of true conditional quantiles. So with these two reasons, we conclude that very likely that the coefficient in QAR for non-causal process are likely to vary and not constant. So this is a very small simulation example to illustrate this idea. So the blue one, so I generate a moving a QAR MAR model of order 1, which one is causal and the other one is non-causal, and the innovations one is exponential distribution and the other one is chi-square distribution. So we can see that the blue one represents the non-causal estimate and the red one represents the causal estimation over the whole quantile range. So we can easily tell that the slope for the causal case is at close to a constant, and the one in the non-causal case actually exhibits a trend, right? From the top to the bottom, we can see there for sure it's not constant. Even
may I ask, what's the tau in the horizontal?
Tau is a quantile. Tau is quantile over 0 to 1. So we run the quantile autoregression over the entire quantile range. So from 0 to 1. And you can see in the causal case, as I explained before, in the null hypothesis, it's going to be constant. And in the alternative case, it should be, if there is non-causality existing in the process, it should be like varying. But what kind of varying, we don't know. But this is one example of varying, like there is a trend. So we just need to test if the coefficient in the QAR case is constant over the entire range to see if there is non-causality existing in the process or not. So this is a very simple linear restriction in the quantile autoregression framework, right? We just need to test that the coefficient is constant over different quantiles. So this constancy test has been developed by the Koenker and Shao in their papers, and we just need to construct a wild statistic based on the estimation or the asymptotic distribution of the QAR estimates. So here we introduce one martingale transformation as it is done in the paper by Koenker and Shao, because we know that the constant is these nuisance parameters of R is also need to be estimated. So this estimation actually can introduce some estimation effect in the final distribution of these statistics. So we implement this martingale transformation to restore the distribution-free attribute of the statistic. And we use the Kolmogorov-Smirnov norm because we need to check to integrate, to employ all information contained in this whole range of quantiles. So that's why we use supreme that to get to the supreme norm of the statistic over the tau over the quantile. And under the null hypothesis, we can conclude that this transformed statistic goes to a p-dimensional standard Brownian motion, and the Ks Kolmogorov-Smirnov statistic also converge to the supreme norm of the statistic. So since we have this test distributional free, and we can just obtain the critical value through an approximation to this asymptotic or limiting distribution by a Gaussian random walk. So there is no difficulty or complicated method in obtaining the critical value in this approach. So there is another approach, which is specification approach based for the test of non-causality. So also driven from the theory one that we can conclude under the assumption 1, 2, 3, which is the assumption for the QAR estimation, and the null hypothesis H0, that the process is causal. We can conclude that the specification of the conditional quantile of Yt is linear across all quantiles from 0 to 1. And with the same assumptions under the alternative, which means the process is non-causal, the QAR, the linear specification, is wrong for the conditional quantile of Yt, at least for one quantile. This has been explained in the previous argument. So that means we can just translate that the process is causal into the linear specification of conditional quantile is correct for all quantiles. and the non-causal process into at least there is one linear conditional quantile specification is run for the conditional quantile of non-causal process. So there has been rich literature about the specification test of conditional quantile or conditional dynamic models, blah, blah. So here we choose two approaches. One is proposed by Escantiano and Velasco in 2010. So they want to test these conditional, they translate this conditional moment restriction, which is required for the specification, correct specification of the conditional quantile into an unconditional quantile, unconditional moment restrictions with the weight equal to the exponential functions. So they constructed these test statistic using the analog, sample analog of these unconditional moments. And intuitively, if this statistic goes to 0 or very close to 0, we can conclude that we don't reject the null hypothesis. But if this statistic is very large from 0 or different from 0, then we can conclude that we reject the null hypothesis, right? And in order to incorporate or integrate all the information contained in the whole range of quantile, we can just employ this Kramer-Von-Mises norm, which is an integration over the condition over the whole range of quantile and the x in the distribution of this process. So we exploit this Kramer-Von-Mises norm, and with the theory it's developed in their paper, we can conclude that under the null hypothesis and assumptions 1, 2, 3, we can get this statistic goes to this one, which is a very complete distribution because we have this estimation of nuisance parameters. So this one is not distribution free, and actually the asymptotic distribution depends on the estimation. So there will be a drift of this final distribution of the statistics. It will be like a Gaussian process with mean 0 and covariant function defined by this this animal, which is super common in quantile regressions. And this drift actually comes from the asymptotic effect of the estimation of that nuisance parameters. So as we have seen that the asymptotic distribution of this approach depends on the estimation. So that means it's infeasible, it's impossible to tabulate the critical value. So in order to get the critical value for the testing procedure, we adopt this subsampling method. So first we have to choose one subsample size, which is B, and then calculate the test statistic, like replicate this same procedure for each subsample, and also their Kramer-Von-Mises form statistic for any given subsample of size B. And we have this for T minus B plus 1, depending on the subsample size that you choose. And we can calculate the empirical CDF of this bunch of statistics and its corresponding sample quantiles, which is 1 minus tau quantile. So the critical value actually is the 1 minus tau quantile of this empirical distribution of the statistics. And once the statistic is a lot greater than this critical value, we conclude that we reject the null hypothesis. And if this statistic is smaller, the original statistic, of course, is smaller than the critical value that we obtain from the subsampling method, then we conclude we don't have enough evidence to reject the null hypothesis that which is the process is causal. So since here there is one subjective choice of bandwidth or the subsample size, which is B. So in the paper by Escantiano and Velasco, they have proposed this choice of bandwidth, which is equal to the largest integer that doesn't exceed this number, which is related to the sample size. And they have checked with some numerical evidence that, or experiments, that k equal to 4, 5, or 6 actually can produce relatively or fairly good performance in terms of power. So in the following simulation, we are going to choose one number, which is 4. Of course, it can be used 5 and 6, but we use 4 to illustrate how this methodology works in the finite sample case. Another approach is proposed by the Escanfiano and Go in 2014. In this approach, the preliminary stages are quite similar to the EB test, which is the one that I explained before. So they translate these conditional moment restrictions for the specification of conditional quantile models into these unconditional moments. Okay, so this is kind of the common procedure, common steps. And then of course, the naive statistic is based on a sample analog of these unconditional moments. So we, again, if this statistic is close to 0, then we can conclude that we cannot reject the null hypothesis. And if this departs from 0 a lot, then we conclude we have to reject the null hypothesis of causality, right? But instead of using the naive statistic of these unconditional moments, they propose that we can implement these orthogonal projection operator to the score function. So that means when you expand this in a Taylor way, expansion way, there will be like a term which is the difference between the estimation of theta and the true value of theta. So in the previous step approach by Escanfiano and Velasco, we denote by EV, okay? They didn't care about this, and they just take into account this estimation effect in the final limiting distribution. But instead of doing that, here EG, let's say Escanfiano and Go, we just here after we call them EG test, okay? They implement this orthogonal projection to kill or to balance the estimation effect from the theta hat. So they implement this orthogonal projection, and then again they also use the Kramer-Von-Misch norm, because we need to take into account all the information contained in the whole quantile range. We get this statistic, and driven from their theory of the asymptotic distribution of the statistic, we can get that under the null hypothesis of causality and assumptions 1 to 4, there is one more assumption needed for this, because in this approach, we need to use kernel estimation for the score function in this orthogonal projection operator. So here we need one more assumption, which is a regularity conditions assumptions for the kernel estimation. So it applied to most of the options. So there is no stringent conditions there. And we can conclude that the statistic goes to this Gaussian process with mean 0 and covariance function characterized by this nasty animal. And the Kramer-Von-Misch form is actually just by applying continuous mapping theory, we could get the corresponding limiting distribution of this statistic. Again, even though we don't have this effect from the estimation or the drift in the final distribution, but still we can see that this distribution, the limiting distribution, heavily or excessively depends on the data generating process. You can see from here that it depends on the expectation of this process. So that means the density function, not just the expectation of the process, but through a very complicated way. That means that the final distribution also relies on the data generating process. Even so, since we don't assume any distributional assumption on the innovations, so we cannot tabulate the critical value again. So there is approach which is to use the multiplier bootstrap to get the critical value. So the steps are following. First, we get we just generate one sequence of RID random variables, which is external. That means it's independent of all the explanatory variable that we use in this process, with mean 0 and variance equal to 1. And then we calculate the new statistic and its Cramér-Von form statistic respectively by just multiply this random variable with the original one. And we can get this new statistic or transform the statistic. It has been shown that the limiting distribution of this transformed statistic is the same as the previous one. So we can just use the empirical CDF of this transformed statistic to represent the CDF of the original statistic and its corresponding 1 minus tau quantile naturally becomes the critical value at tau significance level, right? So once the statistic is larger than this critical value, we can conclude that we reject the null hypothesis. And if not, then we don't have the evidence to reject the null hypothesis of causality. So here, there is one choice of this random sequence of WT involved. So there is a very common choice, which is called like golden ratio. So with this probability, we can get that this random variable is mean 0 and the variance 1. And this is a very common choice. So there is no so with this approach, we try to avoid any subjective choice like the one that we have seen in the EV test, like we have to pick the subsampling size. Here, we don't need to choose any like bandwidth or something. We can just implement this multiplier bootstrap to get the critical value. So in the end, we try to see how these three approach testing procedures like work in the finite sample size case, right? So in the paper, I have for each method where I have different like simulations or experiments. So here, I try to integrate all of them in one simulation case, and we try to compare the three methodologies at the same time to save some time, let's say. So we consider a pair of autoregressive of order 1. One is causal and the other one is non-causal. So the coefficient for the both cases is equal to 0.6, and the innovations vary from 9 types of non-Gaussian distribution, and the one is Gaussian distribution. So in the Gaussian case, we expect that you cannot distinguish causal and non-causal because there is no difference. And in the non-Gaussian case, we expect or we want to see that the testing procedures are able to distinguish causal and non-causal with some relatively or fairly good powers, let's say. So the sample size is 100 and 200. Also, like in the paper, I also have sample size equal to 500. But due to the space of the slides, I didn't include them. And also the replication number is 500. So the critical value is already, how to get them is already illustrated in the previous slides. Like for the constancy test, we just need to simulate Brownian motion by a Gaussian random walk to approximate the critical value, right? And for the EV test, as I have explained, we use subsampling scheme with B equals to 4 times this, the maximum, an integer, like not exceeding this number in the, depending on the size. And for the EG test, we use the multiplier bootstrap. So everything is well explained. So we just report the empirical power and the size in the table 1. So in this table, let's zoom in to see it better. So for the first one, actually for the Gaussian case, we see that, of course, as expected, that we cannot distinguish the causal and non-causal. So the size and the power both should be close to 5% in the close to the nominal level, which is 5%. So once the size increase, the size of sample increase, that the size and power goes to close to 5% of the nominal level for the constancy test and the EG test. But for the EV test, it's a bit weird. I think it's because of the choice of the subjective choice of the bandwidth of the subsampling. So this needs more simulation experiment or Monte Carlo experiment to see how it is sensitive, how sensitive it is to the choice of bandwidth. So this is a main drawback of EV test approach, because you have to pick one bandwidth by yourself, and this could be quite subjective. But for the power, regarding the power, actually in the non-Gaussian distributions, we have seen that all of them actually receive relatively good powers, even especially for the EV test and the EG test, which is a specification-based test. We can see even at 200 sample size, like for the asymmetric distribution, we can see like beta F distribution and the log normal, which we get that quite good size, power, sorry. And also we have tried the sample size increase to 500. We can see that this 40 something becomes like 70 something, if I recall correctly, or 80%. So that means EV and EG test actually, both of them, like they can get the consistency of this test, but EG test is the consistent rate, this rate to the consistency is actually faster if you compare them like parallel. So it's like in the same case, like this exponential, we can see that using EG test, we can already reach the 70%, 75%. And for the EV test, we can only reach 40 something. But once the size increased to 500 case that I didn't report here, or represent display here, that EV test also reached like 70 something percent, and EG test reached like 80 something percent. So we can see that convergence rate is different, but in the end, they are going to be consistent. And we can see that EV test performs better in the case when you have uniform, like this kind of uniform or Laplace distribution. But for the EG test, it outperforms EV test in the case when there's asymmetric, like exponential, gamma, beta distribution. So that coincides with one idea that actually third order moments or fourth order moments actually contribute to the identification of non-causal process. Also, let's talk about the constancy test. There is one fatal problem, is that the size is distorted in the case when there is heavy tail behaviors. So look at log normal or T-student or log normal, or another one that I didn't report here, which is truncated Cauchy distribution. So in those two cases, we can see that the power is really good. The power, even at sample size equal to 100 or 200, the power is close to 100, let's say. But the size is super distorted in the sense that there is over-rejection at the nominal level of 5%. So you can see that the rejection rate or the size is equal to 19 or 20% even in the causal case. That actually comes from a very comes from the volatility of estimation of extreme quantiles. So this can be illustrated by a graph, a graph that I plotted before is here. So this is the QAR estimation of the whole quantiles, and you can see that in the causal case, under the alternative case, which all the coefficients are supposed to be constant, but you can see that when it close to the extreme quantile case, like close to 1 or close to 0, in this case it's close to 1, we can see that the estimation goes crazy. This is reasonable because once that the quantile close to 1 or close to 0, for extreme quantiles estimation, we need more or much larger sample size to get a more stable or less biased estimation. So this is the reason why there is such a huge over-rejection in the constancy test when we try to use this approach to test for the non-causality. Because in the tail case, we don't have enough observation to estimate the parameters like in a very good way, let's say. But EV specification test-based method like EV test and EG test, they're quite robust to these kind of outliers. That's why in the empirical case, like constancy test can be used as a preliminary check, and then followed by either EV test or EG test as a formal check of or conclusion of if there is causality or non-causality. So in the applications, we try to combine the three cases, like either by constancy tests or with EV test or constancy test together with EG test to give a better performance or more precise check of or test of non-causality. So these are the discussion about the results. So we have point out the short drawbacks of these tests and also the advantage of each test. So for the constancy test, in the paper, we also try to use this truncation in the quantiles, since the estimation of quantiles at extreme size can be quite volatile, which can affect the performance of the test, as we have seen that the over-rejection. So we try to implement this trimming or truncation in the quantiles. So we try to get rid of very extreme cases, but this truncation is quite subjective and it's very tricky in the sense if we want to maintain or restore the power of detecting non-causality without this over-rejection. It's kind of tricky in the sense it depends on different cases. So in one case, maybe if we trim at 0.05, that means we start from 0.05 to 0.95. This truncation worked pretty well, but in another case, maybe it doesn't work very well. So it's very subjective in the sense that's why it's not so well recommended in the empirical case, because we don't know the true innovation, a true distribution of the innovation, and we cannot implement a uniform truncation rule for the quantiles for constancy test. But for the specification-based approach, actually, this is quite good in the sense that the size is stable around 5%, and the power is relatively good when we increase the sample size. And one more useful or interesting thing about specification-based approach is that this can be applied or extended to AR process accommodating different heteroskedasticities. So if we have arch model, actually you can just model the arch by the absolute values instead of by the squared values. And with that approach, we can still implement this linear specification test for the non-causality and for the causality. And also from the simulations, actually, we can find out there are some potential research interest that we can do in the further work. Is also, let's go back to the simulation again, the plots here. Actually, the true coefficient is equal to 0. That means 1 over 0 is 1 over 0.6, sorry, is equal to 1.69 or 67 something. So we can see that even though that the linear specification for the conditional quantile of non-causal process is incorrect, but it actually conveys some useful information. We can see when the quantile goes to some extreme case like 0, in this case, we can get actually the true estimation, which is close to 1.67, right, which is 1 over 0.6. And also for the case in the chi-square distribution, we can also see that the estimation close to the quantile equal to 0 is very close to the true value 1.67. So maybe this actually gives us one potential, like potential future like path that we can actually use the information contained in the heavy tails or the extreme tails to extreme quantiles to identify the causal and the non-causal process. But this is kind of just a guess. I mean, we haven't shown like theoretically how it behaves in the extreme case because it's super difficult in terms of statistics and also the derivation of the true conditional quantiles. And also like in the paper, in the application part, that since so far I haven't explained the application part, but I do have one application to one financial series which we suspect there is existence of speculative bubbles, but we try to apply this methodology to more financial series that it has been used in the paper by Sakoyan and the Fries. They use non-causal process to model speculative bubbles in different financial time series, and we try to apply these 3 test procedures into these 6 financial series to see if the methodology actually works in the detection of speculative bubbles. And this is still in process, and I guess this can be done soon. And once it's done, I can include those applications in the paper and make it more complete. And thanks for, these are all the stuff. Thanks for the attention and the attendance, and all the questions are welcomed. Thank you very much.
Thank you, Wei, for interesting talk. Any questions?
Yeah, just one like on the to understand the terminology maybe. So in your terminology, non-causality, for instance, you have a Garch process. So let me put it simple: an Archer-Lem process, an Archer-Lem test, sorry, would be a test of non-causality.
Well, that's why in the beginning, of course, like if we allow for the arch, then actually that can also cause some non-linearity in this like process, and then it could be misleading, right? Because you can reject the null hypothesis because you have arch this process. That's why in the beginning we assume that the innovations follows IID distribution, and we in the last part we try to extend this methodology to the cases where the arch, this type of process, can be also accommodated in the process, and we can still detect non-causality even though there is arch process. So in the simulation, we actually have some like simulation results, like actually we can distinguish arch and the non-causality, but I didn't include in this presentation. But yes, that's a very good question. Like we have to distinguish non-causality and arch type of non-linearity. Exactly.
Yeah. Okay. But so to follow up on that, then so if we have financial return data, so we're surely going to find some arch effects. But then if we take the standardized residuals of the arch, and you can use your procedure to test whether there's some extra dependence that is not captured by the volatility alone. Is that correct?
It's like, yes, you can. I mean, if we use the linear, which I mean, there are many ways to characterize arch type of nonlinear dynamics, right? The most common one is to use the squared value of the residuals, right? And there is another approach, which is to use the absolute value of the residuals. But with the absolute value of the residuals, we can construct this test, like to detect if there is further dependence in higher order moments or further nonlinear dynamics, which cannot be captured by the arch model that is still existing in this process. So that means with that approach, we can still detect non-causality. If we try to model the volatility clustering using absolute value.
And so then one could conclude from the test that there's either forward-looking kind of behavior or that maybe we're missing some external information.
Well, for the testing for forward-looking behaviors, actually, there is one test which is test for the non-invertibility, which is done by Scantiano and some of his co-authors. They use an approach to test that the conditional mean or the error term, not the error, the residual follows martingale difference to test for the non-invertibility. But for the non-causality, there is no such a thing so far in the existing literature.
Okay. Thanks.
Thank you very much for the question.
Any other questions? No? Okay, so thank you very much, Wei, for interesting talk.